In this lesson, we will look at what the standardized normal distribution is and how it is used to calculate control limits in control charts. And hello again to this lesson, which essentially has 3 learning objectives. You will learn how the distribution of values can be described mathematically with the help of the normal distribution. You should then also be able to determine any quantiles of the standard normal distribution using tables or MS Excel. And at the end, you should be able to apply what you have learned by calculating the range between which 99% of the values of a population can be expected. This lesson is divided into 3 chapters. In the first chapter, we look at how the distribution of measured values can be described by the normal distribution. In the second chapter, exemplary quantiles of the standardized normal distribution are determined with the help of tables and MS Excel. In the third chapter, what has been learned is applied to a practical example. Let's get started with the description of the distribution of measured values through the normal distribution. The starting point is again the already known diameter of this piston. It has a nominal size of 60.1 mm. On each of 5 days, 20 samples were taken and the diameter was measured. The measured actual values were entered in the table on the left. An initial distribution of the values becomes visible in the histogram. The height of each bar indicates how often the corresponding measured value has occurred. A typical question in statistical process control is the question of the limits or the dimensions between which all actual values will lie with a 99% probability. For this, you need a mathematical function that describes the distribution of the values as good as possible. This can be in a wide variety of situations, for example, the logarithmic distribution, the Poisson distribution, the Weibull distribution, a mixed distribution, and so on, or even the normal distribution. We can see the formula for the probability density function here on the left and directly on the envelope. To make this formula usable for later practical application, it must first be transposed into its standardized form. This is done simply by setting the mean, mu, to 0 and the standard deviation, sigma, to 1. This completes the equation and x is the only unknown. The expression x minus mu divided by sigma is now substituted by the letter u, but also often by the letter z or t. By substituting with the letter u, one obtains the standardized density function. As a quick reminder, x is the limit we are looking for. To be able to calculate x, the expression x minus mu divided by sigma is equal to u must now only be transposed to x. As can be seen below, one then obtains for the lower limit, x lower is equal to mu minus u times sigma, and for the upper limit, x upper is equal to mu plus u times sigma. The beauty of it now is that you can easily get values for u from existing tables for specific probabilities. The values for the mean and the standard deviation results from the measured values themselves. Now we have everything we need to start the calculations. For a better understanding, a few words about the integral of the probability density. The integral of the probability density describes the area under the curve. The area under the curve is 1 because 100% of all values should be found under this curve. The curve itself starts at infinity and ends at infinity. Therefore, values between 0 and 1 are also given in the tables for the standardized normal distribution. So, if you look for the limit for 99%, you will find it in the table at 0.99, as we will see in the next chapter. And that brings us to the second chapter. In this chapter, we will determine various values for u using MS Excel and a table for the standardized normal distribution. As already explained in the first chapter, u is a factor for the multiple of the standard deviation and depends on the probability with which values should lie before, behind or between limits. The total area under the curve has a size of 1, as we already explained with the integral of the probability density. If you now set limits, the size of the area outside the limits is denoted by the letter alpha. With two limits, the area is divided into 2 alpha halves. Thus, the proportion of values between the limits is only 1 minus alpha. You can also see for which limits we are looking for at the subscript of u. For example, if 99% of all values are between the limits, 1 minus alpha is 0.99 and alpha half is 0.05. Unfortunately, the values for u can only be calculated for one-sided limited distributions or taken from tables. The image here has been adjusted accordingly. The proportion of values outside remains the same with alpha 0.05. The proportion inside or before the limit is then 0.995. The unit for scaling the x-axis is still in millimeters, but will also be adjusted in the next image. So, here the x-axis is now labeled u. The value of u we are looking for is 1 minus alpha, which is 0.995. And it is precisely this value that we will now determine in various ways in the following. From Microsoft Office version 365 or MS Excel, u can be calculated directly with the function norm.s.inf. The function returns the quantiles, this means values for u of the standard normal distribution. As you recall, this has a mean of 0 and a standard deviation of 1. So, if we are looking for the quantile before which 99.5% of all values are, then this corresponds to the 0.995 quantile. The probability input field therefore expects exactly this information. The result for u is the value 2.576. With older versions of Excel, we must approach the result iteratively. To do this, we use the function norm.dist, where x is the estimated starting value for u. The closer this estimated starting value is to the end result, the better. As is known, for the standard normal distribution, the mean is 0 and the standard deviation is 1. The cumulative field must be set to true. Then the formula norm.dist returns the integral of the given formula from negative infinity to x. For the first iteration, create a table. The first column for x with values from 3 to 2.5 in increments of 0.1. In the column next to it, for 1 minus alpha. The result of the calculation just discussed is given. Now you look between which values the probability of 99.5% is to be found. This is the case between the x values 2.6 and 2.5. For the second iteration, the values for x in the first column go from 2.59 to 2.56 in 0.01 increments. This time, the 99.5% probability is between the values 2.58 and 2.57. For the third iteration, in the first column, the values for x go from 2.579 to 2.566 in 0.001 increments. This time, the 99.5% probability is found at the value 2.576. This value is sufficiently accurate and the iteration can be terminated. To save us all the arithmetic work, the values for u for different probabilities have already been summarized in tables. A section of such a table is shown here. If you look for the value of u for 0.995, you look for 0.995 or the value that is closest in the white field of the table, and then read the first part on the left side, here the 2.5. The second decimal digit is read off at the top, here the 8. With this, we have found a value for u of 2.58 using the table. As we know from the previous calculation, the next most accurate value is 2.576. For probabilities that are frequently used in practice, such as 90%, 95, 97.5, 99, 99.5, and 99.99. The values for u are summarized here again. But limits for control charts can also be set for integer values of u. For example, for 2 or 3 times the standard deviation. The probabilities for these values are also summarized here. Compare the probabilities for u, 1.645 and 2. The probabilities of 95% and 97.725% are close together. The probabilities for the values 2.3.6 and 3 are also close together at 99% and 99.8%. Depending on the company or region or country, the specifications can be specified as percentage or in integer multiples of the standard deviation. And so we come to the practical application of what we have just learned. Using an example, we calculate the limits between which all actual values will be located with a probability of 99%. A mean diameter of 60.11 mm and a standard deviation of 0.03 mm were calculated from the measured actual values of 100 samples. The question now is, between which dimensions, x lower and x upper, will all values of the population lie with a 99% probability? As already explained, a transposition to a one-sided distribution must first take place. This is shown on the right. 99.5% of all values are before the limit. The value for u for 99.5% can be read from the table below. As marked in the line here, this has a value of 2.576. This has to be inserted into the formulas for the limits together with the values for the mean and the standard deviation. The result is a lower limit of 60.03 mm and an upper limit of 60.19. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The distribution of the actual dimensions of a product characteristic can often be described by the normal distribution. With a multiplier u for the standard deviation, limits can be calculated between which all values will be located with the given probability. The values for the factors u are given in tables for the standardized normal distribution for one-sided limits. A transposition must be carried out for two-sided tolerances. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care and see you next time. Bye.